material after the first exam that we were looking using Laplace transforms. And if you remember, in the early part of the semester, we would set up our problems if they were linear. If they were nonlinear, we would linearize them. And then we would use methods of ordinary differential equations to solve them. Once we got to chapter 4, we said, you know, the method of ordinary differential equations, that works really well, but there's lots of algebra there. And when we do lots and lots of algebra, we're likely to make mistakes. So maybe there's another way to do the same, solve the problems the same way to get the same answer, but with less algebra. And we saw that the methods of Laplace transform seem to be equivalent to the methods of ordinary differential equations under certain fairly mild assumptions. But what came as a little bit more of a surprise to us, or might have come as a surprise, other than that there was an alternate way of doing things, was that even in order to get the answer, the same answer that we get with ordinary differential equations, we have to invert the Laplace transform. So what we did is we took a time-dependent problem, we Laplace transformed everything, went from the T universe to the S universe, and all the derivatives and integrals disappeared. We manipulated the equations that were just algebraic in the S universe, and we got an answer in S, but we don't care about S. To get the real answer, we had to go back to T. However, what we found was a lot of information we could get about information we're interested in without even doing the inverse to go back to T. To do the inverse to go back to T, we usually had to use partial fractions, of which I wrote one example here of partial fractions with only simple poles. But many times we can get a lot of information relevant for the time domain without even going back to T from the S universe. In particular, we were able to show that because of the final value theorem, we could find the steady state value, if there is one, directly from F tilde by taking the limit as S goes to 0 of S F tilde of S without inverting. Similarly, we could find out issues about stability without even inverting, because we could just look at my answer, which I could write as a numerator over a denominator, and just look at the roots of the denominator, the poles. And because we know that the poles end up in the exponents when I do the inversion, I just have to look at the roots of the denominator, and if I can make sure that they all have negative real parts, then I know it's stable. If there's even one with a positive real part, then I know it's unstable, because when I invert it, it's going to grow exponentially. And there were some more detailed cases that we went through in detail. What we're going to find out now is there anything else we can learn without doing the inversion? And what we're going to look at today is the response of the system to an oscillatory input. That is, where the input oscillates. And in fact, all the information that we're going to be interested in for how the system reacts to an oscillatory input, we're also going to be able to get right from the S domain without even doing the inverse. Now, does that mean you never want to do the inverse? No, sometimes you do if you want to know the detailed behavior of what's happening every second. Then you need to do the inverse. But a lot of times, we don't need that much information. For example, with stability, all we really care about is the system going to blow up or not? Does it reach a steady state or does it blow up? So that information I don't need to do the inverse for, and that's the most important information. I may need other information, but at least that most important thing, do we call the fire department or not, that I can do without doing the inverse. The details of the trajectory, I will need the inverse for. Okay, so why don't we do an example? It's always the best way to introduce an issue by introducing an example. So let's assume I have a CSTR. And this is, again, one of those kind of dumb examples that you only do in control, that you would never really waste your time with in real life, but it illustrates the point. So this is a CSTR, again, with no reaction in it. That's why it's kind of silly. So here's the CSTR, but now the input is going to be I'm going to have, the input is A sine omega t. So I'm going to have as my input, and which variable do I want to be? A sine omega t? CA is A sine omega t. And I want to look at what happens to CA out. So clearly, if this is CA in as a function of t, and here's t equals 0, and now I have a sinusoidal input, A sine omega t, then I would like to know what happens to CA out. For t less than 0, it was at steady state. And now what happens over here? What's the output? So why don't we set that up? If we have the CSTR equation, dCA dt, again, I get a particular pleasure out of writing, well, I'm not going to exaggerate it here, out of writing a ddt, because in none of your other classes do you ever take a ddt seriously in this department. So every time I write a ddt, I'm saying, I'm teaching you, showing you something you ignored in all your other classes. Okay, so here it's just CA in minus CA over tau. There's nothing else because there's no reaction. I could put a reaction and it's not going to change anything. It's not going to change anything significant if it's a first order reaction. But let's keep life simple. So if I rearrange this, I have dCA dt plus CA over tau is equal to CA in, which is now A sine omega t, divided by tau. Now, here the time constant is tau, because there's only mixing, there's no reaction. Obviously, if I had a reaction, it would just combine into the time constant. It would be a t, big T, instead of a tau, but this would still be a tau. So there's really no difference in the algebra. Now let's Laplace transform. If I Laplace transform, and I want to subtract the initial condition. So if the initial, we're given that for t less than 0, CA is, for t less than CA, it is steady state. So I could have dCA t less than 0, so this is t greater than 0 here, and this is t equals 0, dt plus CA t less than 0 over tau is equal to, well, CA in was just a constant. Okay, so do I even need to do that? I don't even really have to do that. Let's just Laplace transform this. So this is being a bit fussy. I don't even have to do that. So let's Laplace transform this. If I Laplace transform this, I get S CA tilde, because that's the Laplace transform of that, plus CA tilde over tau is equal to 1 over tau times the Laplace transform of sine. So if I go to my handy dandy sheet, which you should all have, so why doesn't someone tell me what the Laplace transform of sine is? You're supposed to be having these things with you. You want to tell me what it is?
It's omega over s squared plus omega squared.
Thank you. Okay, so now let's rewrite the left-hand side. If I rewrite the left-hand side, this is CA tilde times 1 plus S tau over tau is equal to that. And now, when I solve for CA tilde, I get CA tilde of S is equal to A omega over S squared plus omega squared. The tau's cancel, and I have a 1 plus S tau. Don't put your sheets away. Now we want to convert this to get CA of t. And, I should have actually been a little more careful. I should have, well, I'm not even going to fuss about it. So what is CA of P? So anyone want to look in the table and tell me what CA of P is? Remember, this is not a monologue. This is a conversation. Do you see anything in the table that looks like 1 over s squared plus omega squared and 1 plus 1 over 1 plus s tab? Everyone should be looking at their table now. And this is a question about reading. And there shouldn't be 1 hour delay to get an answer. So anyone want to tell me what it is? What number line? Line 16. Great. So A omega comes along for the ride. And you notice, well, actually the omega comes along for the ride. Line 16 is exactly this without the A. So I factor out the A, and I can multiply this, and now I multiply it by omega times e to the omega tau, e to the minus t over tau, divided by 1 plus omega squared tau squared, plus sine omega t plus 5, divided by the square root of 1 plus omega squared tau squared, where phi is equal to the arctangent of minus omega tau. Well, that looks complicated, but it's actually not that bad. So let's analyze what we see here. First of all, there's one term that's an exponential decay in t. Remember, the only variable here, independent variable, is little t. Everything else are constants. So this decays exponentially, and this is a sine function. But notice, this sine function is not the sine of omega t, like the input was, but it's sine of omega t plus phi. What does that mean? Well, let's say if phi is a negative number, then that says, let's say phi is minus 2. Then that says, in order to get the answer I got for t is equal to, when the input was t is equal to 2, let's say t is equal to 2 is the maximum here. Here I have to do, omega t would have to be 2 plus the amount that I subtracted off from phi. So let's put numbers in. Let's say phi is minus 10. If phi is minus 10, phi is minus 10, then when omega t was 2, the input was at its peak. To get the peak of the output, I need this thing to also be equal to 2. Well, that means to get this thing equal to 2, I need omega t to be equal to 12, because I need it to make up for phi plus another 2. So what does that tell me? That says when phi is negative, then this peak doesn't occur exactly at the same point, it occurs later on. This peak corresponds to this peak, where the difference is phi, because there's a delay. So notice, in order for this to make sense, the response has to come after the input. So that tells me phi has to be negative. If phi were positive, the response would come before the input. That can't happen, causality. So here the response happens after the input. So is that clear? Here's the input, here's the response. Yes?
So you're saying phi is always negative?
I'm saying for this problem, it's negative. And generally, for these problems, it's negative, and you can see it here, because it's the arctangent of minus omega tau. Omega is a frequency, which is positive, and tau, as long as the space-time is positive, as long as I have a positive volume, then it's going to be negative, and the arctangent of a negative number is going to be negative. So the answer is yes, because of causality. It corresponds to causality. Okay, so now what does this say? This says I have two terms. I don't just have the sine term, but I also have another term that decays exponentially. So the answer doesn't look like this immediately. This is much further down the line. That is after this exponential is decayed. So let's notice the first term goes to 0 as t gets much bigger than tau. So typically when t is about 4 tau, e to the minus 4 is pretty small. You're already just 1% or less than 1%. So when t is bigger than about 4 tau, you can forget about this term. What does that tell me? That tells me that the system sort of forgot what happened before t is equal to 0. We'll see that a little bit later. But what you can see now is that the solution is just a sine function, but whereas the sine function here had amplitude A, the input had amplitude A. Input amplitude was A. That's A. The output amplitude at t much greater than tau is A over the square root of 1 plus omega squared tau squared. So notice omega and tau are both positive quantities, so the output amplitude is A divided by a number bigger than 1. So the output amplitude is smaller than the input amplitude. But it could still be big if omega tau is small. So the first thing we learn here in the analysis is the first term goes to 0 as t goes to infinity. The second thing is that the amplitude changes. The amplitude of the output is different from the amplitude of the input. And the third thing, which we noticed already, is this phi is called a phase shift. That is, if I look long after t is much greater than tau, they're out of phase. So the input is oscillating like this, but the output is oscillating later with a different phase. So it's the same oscillation, but shifted over. The output is shifted over, and the amount it's shifted over in radians is phi. Is that clear? Okay, so now in this problem, it's wonderful. We can actually invert the Laplace transform explicitly and look at the solution and say, wow, that's a really nice solution. However, this was a particularly simple problem. There was no reaction, and it was just the CSTR. What if I have a much more complicated system with reactions and other pieces of equipment that are all hooked together? The chances of it might be a lot of work to actually invert the Laplace transform. I might have to go through this whole partial fraction business. I may need a better table. If I'm unlucky, I may not be able to invert it at all. However, what I claim is that, and what we're going to see now in about the next half hour, is that all the important information about the response to a sine input, that is, what is the frequency of the output? Notice here the frequency of the input is omega. The frequency of the output was omega. So the important questions: what is the frequency of the output? The second question: what is the amplitude ratio? What is the amplitude of the output divided by the amplitude of the input? That's called the amplitude ratio. Make a question mark. I have that already. And 3, what is the phase shift? So those are the 3 questions that I need to know the answer to. Those are the things I really want to know the answer to. Now, of course, that's under the caveat that I'm looking at long times. where t is much greater than the time constant system. Here the time constant is tau, but in general the time constant can be capital T if we have reactions. But I claim we're going to be able to answer all of these questions without inverting the Laplace transform, not just for this simple case, but for any case. Are there any questions on it? And what I'd like to do just before going into the answer is just amplify again what I mean by the phase shift phi. So I'm going to come up with this phase shift phi. Okay, so let's notice, so this is t is equal to 0. To give you a sense of what the phase shift is in this picture, this is a sine function. So if I go from here to here, and here I'm plotting versus time. If I go one period of oscillation, that one period is equivalent to 2 pi, because I go from the same place to the same place. So I've increased omega t by 2 pi. So if I call this distance p, then what I have is that p is equal to omega p is equal to 2 pi. Because remember, this is t, time. And so if I've gone p seconds, then omega p had better equal to 2 pi, because that'll be equal to my phi in that case, if I went full period. On the other hand, let's say I started here, and it took a while to see the corresponding point in the output. So let me call this distance p prime, which is the time it takes, the time lag from the input to get to the same part in phase of the output. Is that clear what p prime is in this picture? Yes? Okay, so phi is related to omega p prime. Again, p prime is in seconds, but we know phi is negative, so I have to put a negative sign. So phi, what's acting here is p prime, which is time, but I have to convert it to radians because it's the argument of the sign. Omega p prime, this distance, is exactly the phase shift. And we know it's negative. So I have phi is minus omega p prime. So now I can solve for omega from here. And I have omega is 2 pi over t. And therefore phi is minus 2 pi p prime over t. So if I want to identify phi from the figure, phi is just minus 2 pi p over p prime. So that's a pictorial representation of what p is. Just sort of a word to the wise, I'm not fussing about people coming on time, but it's sort of like coming in the middle of a movie. If you want to watch a movie and you come 10 minutes late, 15 minutes late, you miss the beginning, and then it's very hard to figure out what's going on in the movie. Similarly here, if you notice, I start the class by introducing what the question is, by going through the connection to the previous classes, what the question is, and then I proceed to the answer. If you're coming in even 5 or 10 minutes late, you miss that, and then you don't really have the connection to the previous classes. I understand in New York City we have subways. Subways have delays. On the other hand, they so frequently have delays that we know what time to leave the class, to leave home, to get here for class on time. It's a word to the wise. Obviously you can do what you like, but my experience is that people who generally don't come to class on time or don't come to class generally don't do well on exams. There's a pretty strong correlation. There are exceptions, there are people who just learn it on their own. But I wouldn't bet that our word was an exception. Are there any questions so far? Yeah?
So P prime is the delay in response?
P prime is in units of time, of how long of the delay in response. phi is in units of radians. So I wanted to just transfer this picture where it makes sense. It's the easiest thing for us to think of is time. So that's why I drew it this way. But so I took the concept that we understand time, that's intuitive, and showed you how to convert it into the phi in the equations. P is on the top, well, because I use blue, invisible blue ink. Okay, I can use pink if you like pink better. Okay, yeah, we just had actually I should use pink since on this Sunday was the breast cancer walk in Central Park and everyone was wearing pink. So in honor of that, I should use the P and prime. How's that? Other questions? Okay, so I think we're ready to do it. In order to do it, I just remind you of some stuff we did of complex numbers, some simple properties of complex numbers that we did earlier in the semester that I don't want to come as a shock to you when I'm doing a derivation. So let's review it again. Remember, we can represent complex numbers as a vector in the complex plane, where the x-axis is the real axis and the y-axis is the imaginary axis. So I could write z, a complex number, as the real part plus I times the imaginary part. Where the real part is the projection on the x-axis, the imaginary part is the projection on the y-axis. If z has an angle theta, that means y is the magnitude of z times sine theta, and x is the magnitude of z times cosine theta. So another way of writing z is z can be written as x, which is z cosine theta, plus I, y, z sine theta. And cosine theta plus I sine theta, we said, is the way we define e to the I theta. So we can write it this way. And theta, as you can see, is the arctangent of y over x. The arctangent of the imaginary part over the real part. So that's just a little bit of geometry. We also, I showed in class, that if I have two complex numbers and I add them, that the complex conjugate of that, the complex conjugate of the sum is the sum of the complex conjugates. Similarly, the complex conjugate of the product is the product of the complex conjugates. And the ratio, the complex conjugate of the ratio is the ratio of the complex conjugates. So I showed this in class. I should have given it for homework, but I showed it in class. And it was just a matter of writing everything out and doing the algebra. Well, if the sum and the products of complex numbers are just the sum and the products of the, if the complex conjugate of sums and products is the sum and product of complex conjugates, then the complex conjugate, then a polynomial, which is just made of products and sums, the complex conjugate of a polynomial is just a polynomial of the complex conjugate. Similarly, the ratio of polynomials, because of this, the complex conjugate of the ratio of polynomials is just the ratio of the polynomials of the complex conjugates. So this follows immediately from here. And that's something I'm going to use. Okay, so in order to show how to extract this information from the Laplace transform, I'm going to start with three assumptions. One, I'm going to assume that the system is stable. If the system is not stable, then I don't really care if it's oscillating, it's blowing up. So if it's oscillating and blowing up, run. Then you don't really care what the frequency of the oscillation is. Blowing up is much more important. So I'm assuming it's not going to blow up. And I know how to analyze that from the stability. Okay, I assume the system is stable. I need to make two more assumptions. The system is stable. The input is A sine omega t. So I'm assuming I have a sinusoidal input. Now, of course, I could have a cosine. I could have a sum of terms, each one of which is sines and cosines. So that's just doing the same analysis many times. And the analysis for cosine is exactly analogous to the analysis for sine. So basically, I'm just assuming I have an oscillatory input. It could have one sine wave, or it could be a sum of sine waves. It doesn't really matter. And finally, I'm going to assume that g tilde of s, the transfer function, is the ratio of polynomials. It's a ratio of polynomials. And now, what I'm going to do is do the problem. And remember, in our problem, we always have that y tilde is equal to g tilde of s, x tilde, where this is the input for the forcing, and this is the output. And this is, of course, the transfer function. And we said it was nice to break it up this way because the transfer function has all the system information, and x has the input information. So in the answer, we're in the S plane, where the S universe, we're separating out the input information from the system information. G tilde has the system information, x tilde has the input information. Well, we know that x tilde by hypothesis, this is x tilde, is a sine omega t. Well, actually, that's x of t. So x tilde of t, we know, is a omega over omega squared plus s squared, because we just looked that up before, you know, when half the class hadn't arrived yet, because it was only a quarter after. Okay, so now let's talk about how to do the inversion. Well, so the inversion, so this is the black line. Okay, so if we want to do the inversion, we have g tilde times x. And remember, when we did these problems beforehand, we said we have an n tilde over d tilde. Here, the assumption is that n tilde and d tilde are both polynomials. What we do is we look at the poles of this. That is, we look at the zeros of the denominator. And then we break it up and handle one pole at a time. If the poles are simple, then I'll just get terms that look like this. If the poles are multiple poles, if they're more complicated than that, then of course we had another expression that instead of m1 over s minus s1, we had a sum of terms that were coefficients over s minus s1 to a power. But we know how to, and we invert those, instead of just getting exponentials, we get t to a power times exponentials. Nothing particularly exciting. But the important thing here is, all of the poles, when they're different, that is, whatever the zeros are of d, they end up segregating into different terms. I get a sum of terms. Each pole gets its own term. So when I invert every one of these, when I invert it, it gives me an exponential. If I have a multiple pole, s minus s1 squared, then I end up getting two terms. One of them inverts to an exponential, the other one inverts to t times an exponential, etc. So the nice thing is it splits up. So that tells me that all the poles of G are in separate terms from the poles of x tilde. So when I do the inversion, I have that y of t. The inversion is going to be a bunch of terms. So I'm going to get a sum of terms, ci e to the sit. Those are for the simple poles. The simple poles are going to look like this. And then I'm also going to get a sum of terms, j, where I also have a subsum, k, di, t to the, dk, t to the k, e to the s, it, sjt. So this is for multiple poles. Remember, when I have a multiple, every root that's a multiple root of the denominator gives me a sum of terms that have powers of t times exponentials. And of course, I could have things that oscillate and decay. So I could have things L of, I need another letter, so B, L of sine e to the, say, alpha plus I omega. So alpha L T sine omega L T plus. So all these things plus the part from the poles of x tilde x. So the part from G tilde has all the kinds of terms that we wrote down before. We had the simple real poles, the multiple real poles, the multiple roots, and then we had the complex poles. And then those are all belong to G. So this is all from G. And then I've got the part from x tilde. So let's just notice, I assume that the system, when I say the system, I mean G tilde, is stable. So what does that mean? If I assume it's stable, that says all the SIs and the SJs and the alpha Ls alpha L are all less than 0. These guys are real, so they're all negative, and the alpha L's are the real parts of the complex poles, they're all negative. So that's by hypothesis, by assumption. That's by hypothesis number 1. So now all I need to do is look at the part that comes from x tilde. So the part from x tilde, well, what's that? Well, that, we just did it. It's A omega. That's A times omega over, and let's factor this. This is S minus I omega, minus a minus I omega, times S minus I omega. Because this is S plus I omega, but I'm being pedantic because I want to let this be S1, like an S1, and this to be like an S2. So here S1 would be minus I omega, here it's plus I omega. And because when I multiply these out, I get S squared, and when I have plus I omega and minus I omega, I get minus I squared omega squared. Minus I squared is plus omega squared. And so when I invert this is, when I invert, I'm going to get A omega times D1 over S minus I omega. Well, forget the inversion. Before I invert, I'm going to do partial fractions. Plus D2 over S minus plus I omega. And now when I invert that, so I broke this up into 2 terms, just as the way I do here. I have this M1 of S and I write it as C1. And when I invert, I'm going to get an A omega times D1 e to the minus I omega plus D2 e to the plus I omega T. Again, because when I have C1, C over S minus SI, when I invert it, I get C times e to the SIT. So whatever SI was, it comes in here. Here SI was minus I omega, so it comes into the exponent as minus I omega. Here SI was plus I omega, it comes in as plus I omega. So I just need to tell you what D1 and D2 are, and then we should be in business. Well, let's notice what D1 is. D1 is just the coefficient here. Well, we know what those coefficients are. That's just M1 over S of evaluated S1. So it's everything in G tilde except this term, this factor, all evaluated at minus I omega. So it's evaluated at minus I omega. And it's everything else. So this is just g tilde s was all of g tilde divided by everything but this factor. So I still have this factor, s minus I omega. And that's just equal to g tilde of minus I omega over minus 2I omega. Similarly, d2 is equal to everything in g tilde, everything except this factor. Well, everything in this quantity except this factor. So that's all of g and the part of s that's left. Yeah. So that's equal to g tilde of s over s, everything but this factor. So it still has this factor, plus I omega, evaluated at I omega. So what's that equal to? That's just equal to g tilde of I omega over 2I omega. Is that clear? I'm just using properties that we've used before. Again, if you expect to understand these things, you really need to get here at the beginning of the class. Otherwise, you jump in the middle and it's all some foreign language. Is this clear? I just followed steps that we've done before. Okay, so let's plug this in. So now I have A omega times d1, which is g tilde of minus I omega, over minus 2I omega, times e to the minus I omega t. That was d1, e to the minus I omega t. Plus d2, which is g tilde of I omega over 2I omega, e to the plus I omega. And now, so this is the, let's remember, this is y of t at long times. Because since we assume that this is all stable, all these exponentials at long times are negative exponentials, they all go away, just like this term went away at long times. So at long times, all I have left is the part from here. So that's what I have here. This is y of t at long times. Where long times, again, means times greater than about 4 times the longest time constant. In this case, there was only one time constant. So it was 4 times tau. But when I have many, many terms, I may have multiple time constants, and it's just the time much longer than about 4 times the longest time constant. So it forgets all these, and this is all that's left. Notice, unlike complex exponent, unlike complex poles, which both oscillate and either decay or grow, purely imaginary poles just oscillate forever, because they're just sines and cosines, not multiplied by exponentials. Okay, so now we're ready to do a little bit more. First thing we can notice is the omegas cancel. The next thing we can notice is we can refer back to what we've done over here. We said we can take any complex number and write it as its magnitude times e to the I theta. So let's let g tilde of I omega be equal to the magnitude of g tilde of I omega times e to the I phi. I'm going to call it phi here instead of theta. It's a little hint. Where phi is the arctangent of the imaginary part of g tilde of I omega over the real part of g tilde of I omega. Because phi or theta is the arctangent of y over x. Y is the imaginary part, x is the real part. Okay, and notice here I have a g tilde of minus I omega. I need to figure out what that is. So g tilde of minus I omega, that's g tilde of I omega complex conjugate, because minus I omega is the complex conjugate of plus I omega. And by hypothesis, G tilde is the ratio of polynomials. So this is the ratio of polynomials of the complex conjugate of something. But the ratio of polynomials of the complex conjugate of something is the complex conjugate of the ratio of polynomials. So by virtue of what we have there, this is just the complex conjugate of G tilde of I omega. Where this is a result of this, which we showed in the previous class. So what does that tell me? G tilde of I omega, I know what that is. That's this thing. This is a real number. Let's put it on the next line. Times the complex conjugate of e to the I omega, e to the I phi. Well, let's notice e to the I phi, or e to the I theta, is cosine plus I sine. When I do the complex conjugate, please keep it down, we're having a class. The complex conjugate of this says I change the I to minus I. If I do that, I just get e to the minus I theta. So the complex conjugate of e to the I theta is e to the minus I theta, e to the minus I phi. And now I can plug in here. So I have y of t at long times is equal to a times, and I'm going to factor out 1 over 2i. Let's do this term first. G of I omega, G of I omega, that's G tilde of I omega, that's this. G tilde of I omega, magnitude. So I've got e to the I phi, e to the I omega t. That's this term. This term has a minus sign here, so I pick a minus sign. This gives me the magnitude, which I factored out, times e to the minus I phi, times e to the minus I omega t. Now, the product of exponentials is just the exponential of the sum. So I just need a plus here and get rid of the e. The product of the exponentials is just the sum, so I just don't need the e there, I just subtract them. And what do I have here? Here I can factor out the I, well, e to the I omega t, e to the I phi. So I'm just going to rewrite it in a separate line so I don't do too many things at once. So I have y of t, t much greater than all the tau is equal to, it's equal to a times the magnitude of G tilde of I omega times 1 over 2i e to the I omega t plus phi minus e to the minus I omega t plus phi over 2i. Let's just rewrite this. Does anyone recognize this from a previous class? E to the I something minus e to the minus I something over 2i. What is that from a previous class? Sine. That is, this is equal to, I have y of t, for t much greater than all the ti's, is equal to a G tilde of I omega times the sine of omega t plus phi, where phi is equal to this thing. No need to rewrite it, just box these two equations. And let's box them in pink. So what we've shown under these fairly general conditions, these quite general assumptions, was that even though G tilde can be enormously complex, it can be this very complicated polynomial ratio of polynomials. As long as it's stable and the input is a sine function with magnitude A, amplitude A, and frequency omega, the output looks exactly like this. Isn't this amazing? The sine omega t plus phi is what we had in this specific case. The amplitude now is, if the input amplitude was A, the output amplitude was A times the magnitude of G tilde by omega. We get a sine function coming out, and we also have an expression for phi. Those are the three questions. Let's go through the questions again. Question 1, what is the frequency of the output? Answers. Question 1, omega output is equal to omega input. It's the same omega. Answer to question 2, what's the amplitude ratio? The amplitude ratio that's equal to the amplitude, the thing multiplying the sine and the output, A magnitude of G tilde of omega, divided by the amplitude of the input, A. So it's just G tilde of omega. All I need to know is G tilde. Whatever G tilde is, it can be some complicated ratio of complicated polynomials. I don't need to invert it. I just plug in I omega. And finally, for question 3, what is the phase shift? Well, it's just phi, just equal to the arctangent of the imaginary part of G tilde of I omega over the real part of G tilde of I omega. So I've answered all 3 of these questions without inverting the Laplace transform, which could be very complicated with G tilde. I get all that information as promised in the beginning of the hour, before half the class was going, without having to convert the Laplace transform. Are there any questions? So the take-home message of that is Laplace transforms, it's hard to invert Laplace transforms, but much of the information you're interested in, you can get without inverting, without solving a differential equation. That's the big advantage of Laplace transforms. Let's say I have 20 CSTRs in series. Do you really want to do the inversion of 20 CSTRs in series? You may not want to, especially since some of them might be in parallel and you may have feedback, as we'll see. Where it's a big mess. This G tilde is a mess. If all I'm interested in is the stability and the response to an oscillatory input, I don't need to invert it. I'll just plug in I omega. And that is an enormous savings. So why don't we do a couple of examples? Any questions? Again, you're always encouraged, not just free to, but encouraged to interrupt with questions. Is your hand up or just an inch?
No, I do have a question.
Or did I provoke an inch?
N1 as a function of S, how does that relate to G tilde of S?
Okay. This thing here, N tilde over D tilde, is the thing you want to invert. So what do we want to invert? What we want to invert is G tilde times X. So, and here I just broke it up into numerator and denominator, but this is the thing we want to invert in general. If I have a simple pole, then I can, that pole is S1, then I can take everything in here except S minus S1. The rest of N and the rest of D, and stick it in, that's just N1. And I take this factor out explicitly. Since it's a simple pole, there are no other S minus S1s, so this thing can be evaluated at S1 and it's finite. There's no zeros in the denominator. And then I know how to calculate S1 and M1 of S, because it's just M1 of S1. It's just this guy, everything else from here set S1, evaluated at S1. And I can evaluate it at S1 because there are no more, it's finite, because there are no other S minus S1s in the denominator. Of course, if it were multiple pole, then I'd have a slightly more complicated form. Now, my hypothesis, I assume that I only have a sine function here, not a sine squared or something. So, therefore, the x tilde broke up into two simple poles, the sum of two simple poles. For each one of those, I could use that formula to figure out what the coefficients are. D1 and D2, I just use them. Here's D1, here's D2. And then I just plugged in and rearranged. I got the answer.
I have a question. For this part, how did you go from exponent minus I and got the omega down?
Are you talking about this line?
Yeah, the 24, how did you go from here to here?
How did I go from here to here?
Yes.
Okay. So I didn't jump from here to here. What I did is I went from here to here. So let's go from here to here. Copy over the A, copy the A. Copy over e to the minus I omega t. There it is, with a minus, over 2I. So this over minus 2I is this over minus 2I over minus 2I. And copy over this, e to the plus I omega t over 2I, e to the plus I omega t over 2I. But I still need to write g tilde minus I omega and g tilde plus I omega. So the term that has the plus, I'm going to write g tilde by omega. G tilde by omega is the magnitude times e to the I phi. Magnitude e to the I phi. G tilde minus I omega, g tilde minus I omega. That's the magnitude times e to the minus I phi. Magnitude e to the minus I phi. Is that clear? And then once I have this, I know that this is just e to the I times omega t plus phi. And this is e to the minus I times omega t plus phi. And then I notice that that's a sine function. Other questions? Okay, well, let's look at an example. Do I have a bigger piece of chalk? Light. Okay, so let's look at one CSDR. And let's do this with, so here's a CSDR where I have G tilde. So we've calculated G tilde in the past, G tilde, so let's add our reaction A goes to B. So this was Kp over the square root, Kp over 1 plus St. We calculated that in a previous class. So why don't we, over 1 plus St, where Kp was equal to 1 over 1 plus K tau, and T was equal to tau over 1 plus K. So that's, we've done that many times. So that's G tilde of this. So that's what we know from previous classes. And now let's calculate these quantities. Well, I don't need to answer question 1 again. Omega is always the same. So now let's calculate the amplitude ratio. Amplitude ratio is G tilde of I omega, magnitude of G tilde of I omega. Kp over 1 plus I omega, S of I omega, T. Let's figure out what that is. That's equal to Kp. That's just a number, and it's a positive number, so I don't have to worry about that. It's magnitude itself. Times the magnitude of 1 over 1 plus I omega. So how do I calculate the magnitude of something? The magnitude over here, the magnitude of z is just the square root of x squared plus y squared. So I need to know what x and y are. That is, I need I in the numerator, not in the denominator. So I want to get rid of I in the denominator, get in the numerator. How do I do that? I multiply by 1. Because I know that 1 plus I omega t times 1 minus I omega t is going to give me something real. So this is just equal to kb times 1 minus I omega t divided by 1 and minus I squared. Minus I squared is plus 1 omega squared t squared. So now I know what the real and imaginary part is. This is kp over 1 plus omega squared t squared plus minus I times omega t over 1 plus omega squared t squared. And I need the magnitude of that, and I lost the kp. So this is equal to kp over 1 plus, and then I need the magnitude. So I'm going to factor out 1 plus omega squared t squared. And now I'm going to take the magnitude of 1 minus I omega t. So I factored out the kp, and I factored out the 1 plus omega squared t squared, and I just have a 1 here minus I omega t. So this is equal to kp over 1 plus omega squared t squared. Now it's the square root of x squared plus y squared. The square root of 1 squared plus minus I minus omega t squared. Well, this is 1 plus omega squared t squared. Square root of 1 plus omega squared t squared over 1 plus omega squared t squared, which is kp over the square root of 1 plus omega squared t squared. So this is the amplitude ratio. Are there any questions on that calculation? How about phi? That's the arctangent of the imaginary part over the real part. Well, I've already calculated the imaginary part and the real part. So the imaginary part is kp times minus I omega, times minus omega t. And the real part is this thing times 1. When I take the ratio, the constants cancel out. And I just have the arctangent of minus omega t over 1. So it's the arctangent of the imaginary part over the real part. I don't need 1. And there's something we can do here called a Bode. So there are two comments I want to make. Comment 1 is, who cares? Well, that's a question. Who cares? So let's see why we should care. Obviously, we care about the frequency of the output because we want to know when the maxima are and when the minima are. So that one's kind of obvious. The amplitude ratio is important because let's say we're doing let's say we're looking at the height of a tank. If the amplitude is so big that it spills over, that's bad. So I want to know what the amplitude of the output is, even if it oscillates. If it oscillates so much that the tank overflows or the tank goes empty, I need to know that. So it's kind of clear why I need to know an amplitude ratio. What's not clear yet is why I need to know the phase shift. And that's going to come when that's going to become clear once we start doing control. We're almost ready to do control because now we're really good at all the analysis, getting good at the analysis. But just let me remind you of an example I gave in the first class why phi might be important. You woke up this morning. You were thinking, oh shoot, I got to go to control. But first I got to go in the shower. So you go in the shower and you turn on the water and it's too cold. So then you turn the hot water a little more and it's still too cold. And then you turn it a little more and then all of a sudden it's burning, so you got to turn it down. Why is that? That's because phi was made. If phi were zero, the minute I turn that knob to hot, the water gets hotter instantly. On the other hand, if I have a big phi, I turn it, I'm still cold, so I turn it again because I'm frustrated. And then once it kicks in, I've turned it too much. So what does that tell me? That tells me if phi is too big, in that case, I'm the control system. If phi is too big, the system's going to be a lot harder to control. So it's a key thing for control. A big phase lag is going to, or big phase shift, is going to make control a lot harder. So you as a control engineer have to work harder to deal with it. So that's why I care about that. Okay, now in part of the analysis, is there too much glare here, or can you see this board? Okay, so last time when I closed one of these, it was enough. Today I'm supposed to do it. Okay. Too bad it's on, there's a nice view of that tree colors. I'll have to see you later. Okay, so there's something called the Baudet plot, which is nothing Baudet plot, which are nice. A lot of times graphs help you understand things. So what a Baudet plot is, there are two Baudet plots. It's just a way of graphing these equations. So it's when I plot the log of the amplitude ratio versus the log of omega, and the log of phi versus the log of omega. So it's just plots of these things. And as we'll see later, these plots help us do control because they're graphical representations, so they make things a little easier to visualize. So let's look at this. Okay, so omega is a frequency. Omega can go from 0 to infinity. If omega goes from 0 to infinity, the log of omega goes from minus infinity to plus infinity. So let's look what happens when, and I'm going to do this right now. I'm going to set kp equal to 1 just to make the figures a little bit simpler or easier to interpret. Obviously, if kp is not 1, I just multiply the y-axis by kp. Okay, so let's look at this. When omega is 0, then the answer is just 1. It's just kp. So 1, so as the log of omega goes to minus infinity, as omega goes to 0, this goes to 1. So there's a asymptote. This eventually goes to 1. On the other hand, as omega goes to plus infinity, when omega goes to plus infinity, this thing goes to 0. So here I have 0, so clearly I have an asymptote on the left of 1 and an asymptote on the right of 0. So that's what this curve looks like. Similarly, if I look at log phi, and I want to look at the arctangent. So if I want to look at the arctangent, first I need to look at the tangent of phi versus phi. So if this is 0, and this is minus pi over 2, and this is plus pi over 2. Okay, well, tangent is sine over cosine. The sine of 0 is 0. Let's say this is 0 right here. The sine of 0 is 0, the cosine of 0 is 1. So the tangent of 0 is 0. So that's correct. The sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So 1 over 0 is? 1 over 0 is? Infinity. So this thing goes off to infinity. The sine of minus pi over 2 is minus 1. The cosine is 0. Minus 1 over 0 is? Minus infinity. So this looks like that. And of course it repeats every half of the period. Okay, so now let's look. When omega is 0, that is the left thing, when omega is 0, this is the arctangent of minus infinity. What's the arctangent of minus infinity in this figure? This is graphing. What's the arctangent of minus infinity? Minus pi over 2. So I'm going to asymptote to here. And when omega goes to infinity, well, I'm sorry, let's do one thing at a time. So when omega goes to infinity, this becomes minus infinity, and the arctangent is minus pi over 2. So I know out here, I'm going to go to minus pi over 2. That's my asymptote. How about when omega is 0? When omega is 0, what's the arctangent of 0? Somebody who hasn't answered yet? Do I have to call on people? People who don't answer, I will call on you. So you might as well volunteer when there are easy questions. What is the arctangent of 0? I can't hear it. 0. So here I have 0. So clearly I know that this is going to look something like this. It's going to asymptote that way. Okay? Well, let's do another example. Let's look at 2 CSTRs in series. 2 CSTRs in series. Well, so G tilde of S is just going to be KP2, I call it 1 plus 2, over 1 plus ST1, 1 plus ST2. Where I'm not going to bother writing out, the KPs are similar and the T's are similar. So the amplitude ratio is equal to the magnitude of KP 1 plus 2 over 1 plus ST1, 1 plus ST2. But it's easy enough to show that the magnitude of Z1, Z2 is equal to the magnitude of Z1 times the magnitude of Z2. So this is homework. So as a result, the amplitude ratio is the magnitude of KP 1 plus 2 times 1 over the square root of 1 plus omega squared T1 squared square root of 1 plus omega squared T2 squared. It's just 2 of these, because each one of these, the magnitude of, so this is I omega. And this becomes I omega. So just the product of 2 of those. And if T1 is equal to T2, then this just becomes KP 1 plus 2 over 1 plus omega squared T squared. So notice, with 1 CSTR in series, I get square root in the denominator. With 2 of them, I get no square root. I just get the whole thing. And similarly, 5, which is the arctangent of the imaginary part over the real part. Well, that I have to figure out exactly what that is. So I still have to calculate the imaginary part and the real part. So why don't we do that for the case when T1 is equal to T2? If T1 equals T2 is equal to T, then I have KP 1 plus 2. And here I have 1 plus I omega T1, 1 plus I omega, 1 plus I omega T squared. Because I'm looking at the case of T1 equals to T2. In that case, I multiply this by 1 minus I omega T squared and 1 minus I omega T squared. Because each factor, when it multiplies by this, becomes real. So this thing, so this is G tilde of I omega. So this is KP 1 plus 2. And the denominator becomes exactly the square of this denominator. So nothing's changed there, because I know that 1 plus I omega T times 1 minus I omega T just gives me 1 plus omega squared T squared. And that gives us T squared. That is, each one of these is this product. And I have that product twice, so I get this thing quadratic. But the numerator is 1 plus I omega T squared. So let's figure out what that is. That's 1 squared, plus I squared omega squared T squared. I squared is minus 1 omega squared T squared, plus 2I. Actually, let's write it out. So I have 1 minus I omega T times 1 minus I omega T. So I have 4 terms. I've got 1, I've got this thing times this thing, which is plus I squared minus omega squared t squared. And then I have minus I omega t minus another I omega t. Minus I times 2 omega t. So if I haven't made any mistakes, I just get that. Okay, so that this algebra tells me that now all I need to do for phi is I need to take the arctangent of the imaginary part over the real part. Again, since I'm taking the ratio, the coefficient of that factors out of the real part and the imaginary part is both the numerator and denominator, so it cancels. So what I have here is the arctangent of minus 2 omega t divided by 1 minus omega squared t squared. The amplitude ratio is so again, how did I get that? I took g tilde by omega, which I need to do here. To get the amplitude ratio, I need the magnitude of g tilde by omega. I plug in g tilde by omega, that's this. I notice I have i's in the denominator, so to get rid of them, I multiply by the complex conjugate of the denominator, of the original denominator, divided by itself. That gives me this in the denominator and this in the numerator when I multiply this out. And I take the arctangent of the imaginary part over the real part. The imaginary part over the real part. And that gives me the phi, and I know the amplitude ratio, and I know the magnitude. Are there any questions on that? Questions? Okay, and from that, we just need to make the Baudet plots. And why don't we just finish off with those Baudet plots, and let's do them in a different color. Okay, so part of it is easy. So for example, notice, let's do the amplitude ratio for this case. When omega goes to 0, again, I just get 1. So I still go to 1 here. However, when omega goes to infinity, I again go to 0. So it doesn't look like a big difference here. When omega goes to 0, this thing becomes 1, if kp is 1. And when omega goes to infinity, this thing goes to 0. So the amplitude ratio looks similar, has similar asymptotes. So I'm not even going to draw it. Actually, the way it goes down is a little different because it goes down a little quicker. But again, I'm going to have similar asymptotes. How about the arctangent? When omega is 0, again, I have the arctangent of 0. So the 0 limit is the same. The minus infinity limit is the same. But what happens when omega goes to infinity? When omega goes to infinity, the numerator goes, so this drops out, the 1 is irrelevant. And when omega goes to infinity, I still have an omega in the numerator and omega squared in the denominator. So when I have the omega squared in the denominator wins, and this thing still goes to 0, and the arctangent of 0 is still 0. So, so let's just notice the arctangent of 0 is 0, and the arctangent of, and this corresponds to omega goes to infinity. And when omega goes to 0, it's the arctangent of 0 is equal to 0. So let's just check it again. When omega is 0, I have the arctangent of 0, and when omega is infinity, I also have 0. So clearly, it has an asymptote over here of 0 and an asymptote over here of 0. And what does it do in between? In between, it's the arctangent of a quantity that we have to figure out. So I'll just leave that for next time.